Oh, so the last lecture today is by Arul Shankar from Toronto. Title is Average Rank of Elliptic Curves, Overview and of the Result. So please.
Thank you very much. Thank you very much. And it's a very great pleasure to speak here. I wish I could have been in person, and hopefully next time I will be. But I'm very happy. But I'm very happy to be here, at least remotely. Okay, so let me just share screen and begin right away. Okay, so this is the first in a series of 4 lectures. And so I want to start by saying that everything I talk about is going to be joint work with Manjul Bhargava. I'll also mention some other results and with other people, in which case I'll cite it at the results, but most of what I talk about is just going to be joint work with Manjul. Okay, so the topic here, like essentially what we'll be talking about are elliptic curves over the rational numbers. So we're going to be looking at elliptic curves over Q. And every elliptic curve over Q can be written in the form y squared equals x cubed plus ax plus b, where a and b are integers, where this cubic polynomial x cubed minus ax plus b has distinct roots. So we will require the condition delta a comma b, which is minus 4a cubed minus 27b squared, to not be 0. That's the discriminant of the cubic polynomial. And we will also require the following condition in order to make sure that this is actually a unique representation and that every elliptic curve only shows up once when I write it in the form y squared equals x cubed plus ax plus b. And that condition is that if p to the 4 divides a for any prime p, then that should imply that p to the 6 does not divide p. This should hold for all primes p. And if this is true, then every elliptic curve can be written uniquely in this form. And we will write E to be the set of all elliptic curves. Okay. So we know from basic theory that we have a group law on the Q points of E. And here, of course, I'm including the point at infinity, which will be the identity element for this group. So this gives us an abelian group. And our story today starts with a result of Mordell, which says that this abelian group is in fact finitely generated. So that's a classical theorem of Mordell. And what it implies, if you combine this fact that E of Q is an abelian group which is finitely generated with the classification theorem of finitely generated abelian groups, we'll see that E of Q is isomorphic to T direct sum Z to the R, where T is a finite abelian group and R is some non-negative integer and R is called the rank of E. So maybe I'll write R of E. So that's the definition of the rank. Because E of Q is finitely generated, you can write E of Q as T plus Z to the R, and that R is the rank of E. Now, there are very deep questions that one can ask about both the torsion part of an elliptic curve as well as the rank. So let me in fact start with this incredible result of Barry Mazur's, which says that T has only finitely many possibilities. So T is either Z mod NZ for 1 less than or equal to n less than or equal to 12, less than or equal to 10, or n equals 12, or it could be a Z mod 2Z cross a Z mod 2NZ for 1 less than or equal to n less than or equal to 4. So it's a very small set of possibilities for T. So it's a very deep result that this is true. And today we're going to be concentrating more on the rank. Now the rank is another extremely mysterious object. So for example, we don't have an algorithm that's known to terminate that determines the rank. It's been a question for nearly a century as to whether the rank of elliptic curves is bounded or not. And people believe yes, then no, then yes, then no. And today we believe yes because of some really beautiful heuristics. So we believe, so there are heuristics due to Park, Poonen, Voigt, and Wood, which suggest that the rank is absolutely bounded. The largest rank elliptic curve that we know is a rank 28 elliptic curve that was constructed by Noah Malkis. I think that's still the record. But what we're going to talk about today is a kind of questions that are in a slightly different flavor, because we're not going to be talking about what happens to individual elliptic curves, but rather we're going to ask about how the rank behaves on average. So how is the rank distributed? So we want to be able to phrase average statements on elliptic curves. And to do that, we have to take the family of all elliptic curves and order them in some way. So we're going to order elliptic curves in our family E by what we call the height. And this height is pretty simple. So suppose E is, if you'll recall, we've written it as y squared equals x cubed plus ax plus b. We're just going to define the height to be the maximum of 4a cubed and 27b squared. So if you'll recall, the discriminant was minus 4a cubed minus 27b squared. We would love to order elliptic curves by discriminant, but that turns out to be a very difficult question. Like even counting the number of elliptic curves with bounded discriminant is highly non-trivial. So instead we order it by height, which is sort of defined in a way to almost mimic the discriminant. And we expect that whether you order elliptic curves by height or by discriminant or by conductor even, you'll really get the sort of statistics will remain the same. But for today, we're going to be ordering elliptic curves by height. And once we have this ordering, we can talk about average values. So for example, suppose f is some function on the family of elliptic curves. So it could be the rank, it could be the size of the torsion group, it could be any function. For any function f on the set of all elliptic curves, we define the average of f to be the following. First, we take all elliptic curves with height less than x for some large number x, and we'll sum f on these elliptic curves, and we'll divide by the number of elliptic curves with height less than x. And then we'll take the limit as x tends towards infinity. And if this limit exists, we say that the average of f is equal to this limit. And so that's the way of talking about, because now that we have a height function, that's the way of discussing average values of various functions that you might want to define in elliptic curves, various natural quantities of elliptic curves. So it's a very nice application of Hilbert irreducibility. I won't really prove it here, but I won't prove it here. But what it says is that 100% of the time, that finite group T, if you'll remember, we wrote E of Q as T, which is a finite abelian group plus some power of Z. So Hilbert irreducibility very quickly implies 100% of the time, this group T is trivial. So most elliptic curves don't have non-trivial torsion. So for most elliptic curves, E of Q is simply Z to the R for some R. So the study of average values of T is not very interesting. So what we're going to do in this talk is we're going to consider the following question, which is, what is the average value of the rank? Okay, so it's a conjecture. Conjecturally, we know what to expect. And this conjecture is due to Goldfeld and Katz-Sarnak. And this conjecture tells us how ranks are distributed amongst elliptic curves. So what this says is that 50% of elliptic curves have rank 0. 50% have rank 1. Now the remaining 0% is still going to be an infinite set, but the conjecture is that this 0% doesn't actually interfere with the average rank. And so the last part of the conjecture is that the average rank is a half. Okay, so I'd like to say a few words about why we expect this conjecture to be true. One really excellent explanation for this was given by Maser, which is why this is called the minimalist conjecture. So let me try and convince you why you should expect this to be true. So if you'll recall, given an elliptic curve E, you can attach to it an L function. And if you complete this L function, you get some, I don't know, you get some completed L function, which satisfies a functional equation. Now I'm going to normalize the functional equation so that S goes to 1 minus S. So the functional equation looks like lambda E of S equals lambda E of 1 minus S times some quantity which is called the root number. Now the root number of an elliptic curve is defined as a so it's either 1 or minus 1, and it's defined as a local product of local root numbers. The product is over all places of Q. And these local root numbers are defined essentially by congruence conditions on the coefficients of E. And so, like with all these sort of, you can think of the root number of E as being something analogous to, for example, the Mobius function on square free integers. And in particular, what we expect, even though we do not know how to prove this, we expect that half the time it's 1 and half the time it's minus 1. There's no reason to expect anything else. So we very strongly expect that this root number is going to be 1 half the time and minus 1 the other half of the time. However, note that when the root number is 1, the order of vanishing of this L function at the critical point is even because of the functional equation. The functional equation takes S to 1 minus S. So in particular, it takes half to itself. And so if the root number is 1, then the order of vanishing must be even. So it's either you have a pole, either you don't have a pole, or you have either you don't have a 0, or you have a 0 of order 2 or a 0 of order 4, or so on. And conversely, when the root number is minus 1, then the order of vanishing is odd. Now, why do we care about the order of vanishing of these L functions? Well, because of the BSD conjecture. So the Burge-Swinnerton-Dyer conjecture states that the order of vanishing of lambda ES, which is called the analytic rank of E, is equal to the algebraic rank of E. So the Burge-Swinnerton-Dyer implies that the order of vanishing is exactly equal to the rank. And so we expect, because we expect the root number to be equidistributed, that the ranks of elliptic curves are even half the time and odd half the time. Now, suppose you also believe that it's very rare for a curve to have more points than it's forced to, then you should believe that whenever the root number is 1, 100% of the time, the rank is 0. And if you take the family of elliptic curves, the root number is -1, then 100% of the time, the rank should be 1. And so if you believe in minimalism, which is to say, on average, there are as few points as possible. If you believe in minimalism and you add to it BSD, and you add to it the fact that the root number is equidistributed, what you get is the Goldfeld-Katz-Sarnak conjecture. So you get that 50% of elliptic curves must have rank 0, because those are the 50% with root number 1, and 50% have rank 1, and those are the curves with root number -1. So hopefully I've convinced you why we expect this conjecture to be true. And now I want to move on to some results. So first of all, I should say that the analytic rank of elliptic curves has also been very well studied. The analytic rank of elliptic curves has also been extremely well studied by many people. So let me tell you something about the average analytic rank. So to study the analytic rank, it helps to assume the GRH. So assume the Riemann hypothesis for L functions of elliptic curves. Then the average value of the analytic rank has been proved. And remember, just like the algebraic rank, we expect the analytic rank to be equal to the average ranks. We expect this to be a half, but it's proved to be less than or equal to. So it was successively bounded by works of Brumer, Heath-Brown, and Young. So Brumer proved that it was bounded by 2.3. Heath-Brown improved this bound to 2. And finally, Young improved this bound to 25 divided by 14, which is around 1.79. And this result, I mean, like they're assuming the generalized Riemann hypothesis on these L functions, and they're studying its critical value. They're studying its value at a half. What is the reason we might want to believe in minimalism? I mean, it's like having points on curves is usually very, very rare. Yeah, so I mean, like, unless you have a very good reason, so for example, if you're a conic, then you can write down all these points. So unless you have them, unless there's some good algebraic reason for points existing, usually they don't exist. Okay. So these are sort of pretty amazing results. In particular, if you also assume PSD, then this also tells you that the average rank, the average algebraic rank is bounded. And in particular, this final bound of 1.79 of Young takes us a little bit towards the Katz-Sarnak conjecture, which is that, it tells us that at least a positive proportion of curves must have either rank 0 or rank 1. I do not know of any unconditional bound on the analytic rank. It's a very good question, but yeah, I don't know. I mean, I might have I'm not, doesn't, I mean, it might still exist, but I have not seen a bounded analytic rank which is unconditional. That's a good question. That's good. That's a very interesting problem. Okay. So that's one way to study ranks. I mean, remember, the BSD conjecture is telling us that on the one hand, the analytic rank, and on the other hand, the algebraic rank, they're equal. So, I mean, studying one should imply understanding the other. And there's this wonderful approach by studying families of L functions to study the analytic rank. But for this talk, for the series, we're going to talk about the algebraic approach to studying ranks. So we are going to study the algebraic ranks via studying Selmer groups. Now, the next lecture is going to be devoted to studying Selmer groups. So I won't define them now. I'll define them next time. But for now, I'll just tell you the most important fact about Selmer groups that we're using, which is that it fits into the following exact sequence. So for any integer n greater than or equal to 2, we have the following exact sequence: EQ mod n EQ injects into what's called the n Selmer group of E. I haven't told you what it is. I'll tell you what it is tomorrow. But for now, you can just, instead of take this exact sequence as a definition, which maps into the n torsion of the Tate-Shafarevich group of E, which maps to 0. So this is an important exact sequence. And the point here is that the n Selmer group of E is a finite group. And in fact, this was Model's insight. This was how he proved that ranks were finite. It's that, I mean, the difficulty in studying rational points in elliptic curves is that they can have really huge height. So you might have a curve, its coefficients might be small, and you might say, okay, I'll just do a search for rational points and see if there are any nearby, and you might find nothing nearby, but it doesn't say anything about the points because the points can have very large height compared to the coefficients of the elliptic curve. So basically, trying to understand this quantity E of Q mod n E of Q is quite difficult because it's hard to find small height generators for the ranks of elliptic curves. For small rank generators for the group E of Q. However, the Selmer group is much easier to control. So the whole idea here is going to be to study n Selmer groups of elliptic curves. And the main result that we're going to be focusing on is the following result due to myself and Manju Bhargava. Which is that suppose n is 2, 3, 4, or 5. Then the average size of the n Selmer group of elliptic curves equals the sum of divisors of n. So in particular, the average 2 Selmer group is 3. The average size of the 3 Selmer group is 4. The average size of the 4 Selmer group is 7. And the average size of the 5 Selmer group is 6. So, okay. So we can use these Selmer group bounds to immediately bound the average rank. So in particular, let me use, so of all these, I mean, like, in fact, as n grows larger, it's sort of, you get better and better bounds on the average rank of elliptic curves. And here n equals 5 gives us the best average rank of elliptic curves. So let me talk about the n equal to 5 case. So the point here is that we just, I mean, like, 5 to the rank of E by the exact sequence is less than or equal to the size of the 5 Selmer group of elliptic curves. So on average, what we see is that, so we use the fact that 20R minus 15 is less than or equal to 5 to the R for all R. You can check this. And this implies that the average rank is going to be less than or equal to 6 plus 15 divided by 20, which is 1.05. So immediately, just by inputting this result, when n is equal to 5, tells us that the average rank is finite and that it's bounded by 1.05, which is pretty good. It's not anywhere near the truth, which should be 0.5, but 1.05 is still pretty small. Okay, so let me tell you how we can improve this result. So I mean, the remainder of this series in the next 3 lectures, we'll be talking about the proof of this theorem. We'll be talking about just how to control the average sizes of these Selmer groups. However, for this talk, I want to talk about a few applications of the theorem. So I want to talk about, so we've already seen now that because the average rank is the average size in the 5 Selmer group allows us to bound the average rank by 1.05. But it turns out that we can improve this quite a bit. So here's how we're going to improve it. So we first begin by observing that this 1.05 is achieved when 95% of elliptic curves have rank 1 and 5% have rank 2. Because you see, I mean, what we know is that the average size of 5 to the rank of E is bounded by 6. So from that, you only actually achieve an average rank of 1.05 only if 95% of curves have rank 1 and 5% of curves have rank 2. However, this is very unlikely to happen. We know this is unlikely to happen. One of the reasons we know this is unlikely to happen is that we believe that the root numbers are equidistributed. So we believe that half the elliptic curves should have rank even and half of them should have rank odd. So it's very unlikely that 95% of them are going to have rank 1. So how do we use that fact? What we do is, I mean, like, if you believe the BSD conjecture and you believe, so I mean, if you believe the BSD conjecture, then you can say that, well, if the root number is odd, then if the root number is 1, then you must have a curve with even rank. But we don't, unfortunately, know the BSD conjecture. However, we have this incredible result due to Dogchitzer and Dogchitzer. And this incredible result says that the P-Selmer rank for any prime P is even if and only if the root number of E is 1. So the 5-Selmer group is a 5 group. It's a group of, and its rank, according to this wonderful result of Dogchitzer and Dogchitzer, is even if and only if the root number is 1. So if we construct a lot of curves with root number 1, we believe that 50% of curves have root number 1, but if we construct a lot of curves with root number 1, anything greater than 5%, what that's going to say is that the P-Selmer rank must be even, which means you can't be in the situation where half of them have rank, where 95% of them have rank 1 and 5% of them have rank 2. You sort of prove that you have lots of curves with even P-Selmer rank. So we improve our bound by proving that the root number is 1 very often. Now, unfortunately, controlling the root number is quite a difficult thing to do. So it turns out that, let's just assume for simplicity. So we know that, so I mean the point is that the root number of E is going to be a product of local root numbers. And this, so like, if E has good reduction, then the root number is the local root number is just going to be 1. But if E has multiplicative reduction, then the local root number is going to be 1 if the reduction is split, and -1 if the reduction is non-split. And telling split reduction away from non-split reduction is a very difficult thing to control on average. So that makes it quite difficult to control the root number. So what we use here is an idea due to Simon Wong, which is, it's the following, it's a very beautiful idea of his, which is essentially that if you take, you take an elliptic curve E, and then you take its twist by -1. Now, these two curves have the same height. And what's more, it's very easy to compute the product of their root numbers. It's very easy to see how much the root number changes if you twist by -1. it's much less subtle than controlling the root number of E itself. And so if you do this explicitly enough, it's possible to prove that there's a very large family of elliptic curves in which the root number actually equidistributes, because you can prove that very often. So let's call this W of E times W of E twisted by -1. Let's call it D of E. So we prove that there exists, I don't know, something like 55% of elliptic curves, or like saying there exists. I mean, there's a family which consists of about 55% of elliptic curves. D of E is -1. So for this very large set of elliptic curves, if you twist by -1, the root number changes. Now they have the same height. So this produces lots of curves with both root number 1 and root number -1. So it's actually possible to prove that lots of elliptic curves do have root number 1 and do have root number -1. And so you can use this wonderful result of Dockchitzer and Dockchitzer, which says that in that case, you have lots of elliptic curves where the P-Selmer rank is odd and the P-Selmer rank is even. And so putting all of this together, we can improve our results. So let me state the consequences. So the result, which I should say this application of this Phi-Selmer bound along with this root number equidistribution gives us the following result due to Manchul and myself, which is that when elliptic curves over Q are ordered by height, the average rank is actually less than 0.8826. And that at least 20.92% of them have rank 0. And that at least 83.81% of them have rank either 0 or 1. Okay. So let me continue now with a very short overview of the proof. So I mean, we've seen already how to get these average rank results, and they follow essentially, they follow from this average size of the Selmer group result when n is equal to 5. So what I want to do for the remainder of this lecture series is just talk about how this theorem is proved, how we compute the average size of Selmer groups. And the proof of this result is really in 3 parts. So it's in three parts. So the first thing is, okay, so we have Selmer groups of elliptic curves, but we want to get a handle on them. Like, how do you actually work with Selmer groups? How do you average over Selmer groups of different elliptic curves? So the first thing we're going to do is, when n is 2, 3, 4, and 5, we're going to construct a semi-simple group Gn and a representation of it. So this representation is going to be co-regular. In fact, more than co-regular, it's, the polynomial invariance. So when I say co-regular, what I mean is that the polynomial invariance for this action . So co-regular just means that if you take the polynomial invariants for Gn and Vn, they should be freely generated. The ring of polynomial invariants should be freely generated. And in this case, it's going to be freely generated by two elements. So for each n, we're going to construct the semi-simple algebraic group Gn along with a representation of it. Yes, that's a very good question. Why only up to n equals 5? Exactly. So the n greater than 5 cases are indeed open. And the reason they're open and the reason they're much harder than the n equals 2, 3, 4, 5 case is this crucial ingredient is missing. So our first step is going to be this construction of a group Gn acting on Vn, which parameterizes Selmer group elements. And we haven't found these groups for n greater than 5, which is why those are the ones that are still open. That's, to make progress on those, we first need to, it would be helpful if you could find these representations. But for n equals 2, 3, 4, and 5, these are classical representations, classical co-regular representations that have been studied. And the point here is that the polynomial invariants for the action are going to be freely generated by two elements. And I'm going to give these two elements a name. Let's call them I and j. There are going to be two polynomial invariants for each of these called I and j. When n equals 2, we'll be able to write down what I and j are. When n is equal to 5, we won't be able to write them down. We just know they exist, but they'll be extremely complicated. But whatever, there are going to be some two elements, I and j. And what's going to be true is that if we take the elliptic curve, so I'm going to call it EAB, then we'll be able to take the n-Selmer group of EAB and inject it into the set of GNQ equivalence classes, GNQ orbits on VNQ. What's more, the invariants of these orbits that correspond to EAB will depend only on A and B. So we look at VNQ, we look at GNQ orbits on VNQ. So the image is going to be contained inside orbits with invariants A and B. So the n-Selmer group of an elliptic curve EAB, we will be mapping it inside these rational orbits with invariants A and B. So this step of the proof is called the parameterization step. So we're going to do this next time. And I mean, and very crucially, what we will prove is that every such orbit has an integral representative. So, I mean, like the issue is you have some random orbit with invariants A and B. It's a rational orbit, but it's not so bad. This orbit is going to have an integral representative. So it's going to be enough to consider V and Z. We don't have to worry about V and Q, which is much harder to control. So we'll need to study, we'll need to understand G and Q equivalence classes on V and Z, which is a much easier question than understanding G and Q orbits on V and, because there are too many Q points. But V and Z is a nice lattice. So step 2, so 3 lectures left, 3 steps in the proof. Step 2 is the counting step. In this, here, what we're going to do is we're going to define a height on V and Z. This height is going to be G invariant. And the goal of this step, the entire goal of this step is going to be to count the number of G and Z orbits on V and Z having height less than X. So we'll define a natural height on V and Z, and we will count the number of G and Z orbits on V and Z which have height less than X. And that will take us much closer to our result. However, there are crucial differences between what we need and what we have. Like even if once we've counted G and Z orbits on V and Z, there are still crucial differences, which is, first of all, we want to study G and Q equivalence classes, not G and Z orbits. Secondly, this is merely an injection. This is not a bijection. So we're not counting all orbits. We only want to count certain orbits, and we don't even want orbits. We want equivalence classes. We want Q equivalence classes, not Z orbits. So step 3 will be relating the number of these orbits in terms of the number of equivalence classes, and what's more, counting only. So step 3 is going to be, I mean, so step 3 will finish the proof, but what we will have to do here is we will need to count orbits that satisfy infinitely many congruence conditions. And we will do this via a sieve. And once we've carried out this sieve, we will recover our main results using a mass formula. So those are the three steps of the proof. There's the parameterization result, there's the counting result, and then there's the sieve, which along with the mass formula will give us our main theorems. And we will, each of the remaining 3 lectures will be devoted to a step. We'll first do the parameterization, then the counting, then the sieve. And so for now, let me stop talking and take any questions if there are any.
So first, let's thank the speaker. Any question?
Oh, that's a wonderful question. So there's a question in the chat which says, do we know similar results for average ranks of elliptic curves over arbitrary number fields? So we do. These Selmer results, and this is due to work of Manjul Bhargava, Jerry Wang, and myself, which is that these Selmer averages are in fact known not just for elliptic curves over Q, but for elliptic curves over every function, over every global field. So if you have any global field, then you can prove these results. And they give a bound on the average rank. So we can prove in particular that the average rank of elliptic curves over any global field is bounded by 1.05. But the dogsheet the result doesn't carry over, so we can't improve it using root number considerations. But we do have that the average rank for elliptic curves is bounded by 1.05 for elliptic curves over any global field.
Well,
that's it. Oh, sorry.
Any other question?
So there's one more question in the chat, which is about the role that Shaw plays. That's really an excellent question. So let's go back to the exact sequence. Here's the exact sequence. And this is what we want to understand perfectly in order to understand the average rank. This is what we are able to study. And you're absolutely right. The Tate-Shafarevich group does contribute, which is why from the Selmer averages, we won't get the exact rank bounds. Because the Tate-Shafarevich group has a non-trivial contribution. So like the distribution of the ranks are different from the distribution of the Selmer ranks. And in fact, there are beautiful papers that develop heuristics for all of this. The paper of Poonen and Rains that sort of conjectures how how P-Selmer groups of elliptic curves should be distributed. And then there's a paper due to Bhargava, Lenstra, Poonen, Rains, and Kane, in which they conjecture how this entire exact sequence should be distributed. How should Shaw be distributed? How should the Selmer group be distributed? How should ranks be distributed? They put it all together. And Shaws definitely get different. They have a non-trivial contribution. You're absolutely right. Another excellent question. What about the quadratic twist family of a particular elliptic curve? That's a really excellent question. I was going to talk about it a bit more tomorrow when I define Selmer groups. But in fact, this conjecture is due to Goldfeld and Katz-Sarnak. And Goldfeld conjectured it for families of quadratic twists of a particular elliptic curve, while Katz and Sarnak conjectured it for the full family of elliptic curves. Now, the Goldfeld conjecture is for twists of an elliptic curve. It has been solved by Alex Smith. It's recent, extremely groundbreaking work of Alex Smith, which comes very close to proving the Goldfeld conjecture. And he does it by understanding the 2-Selmer group, the 4-Selmer group, the 8-Selmer group, or the 2-infinity Selmer group of elliptic curves of a quadratic twist family.
Okay, so please, the question from the audience.
Over function fields, do some aspects differ?
Not on average, no. That's a very good question. I mean, over function fields, there are like depending on the questions you ask, for example, the rank boundedness conjecture of Park, Poonen, Voigt, and Wood is something that doesn't hold over function. It's something that's just not true of function fields, because you can construct families of elliptic curves that have unbounded rank. But there are very few of them. They're very special families. So they don't really contribute to the average rank. So the average ranks, they all stay the same. We expect.
Any other question? Okay, so let's thank speaker again. So this is the last lecture. See you tomorrow.
Thanks very much.